Hello everyone, today I would like to talk about multiplexing. The first question is what the multiplexing is. Whenever we have different sources of the information or different kind of data, and we would like to communicate them through a channel, a specific channel, so we are encountering limited resources, we do need multiplexing. We should add them together and communicate them, send them through the channel. This is the multiplexing, and the reverse of act of that is demultiplexing. We have three basic techniques for that. The first one is assigning different frequency to each one, which is frequency division multiplexing. The second one is assigning different time for the communication, and the third is assigning different codes. In this video I would like to talk about frequency division multiplexing. What is frequency division multiplexing? Imagine these are our data, different waveforms, and for each one we do need a carrier, different carriers, and we should add them together. Actually, we should mix them together, and then the summation of them will go through the channel. And why SSB? We do need that as a single sideband. What will happen? The data is a cosine function, so when we multiply two different cosine to each other, we will end up with two different carriers, or two different impulse response. I'm going to show you on the software. And this one, which is the upper sideband of that, will occupy more bandwidth, which is unnecessary, and we should consider that as an unwanted signal. So we will filter this one and call it as a single sideband or suppressed carrier, and we'll send this one. Okay, let's go back. For that reason, I've chosen two different signals, F1 and F2, or F message 1, message 2, and two carriers. And we know that the carrier frequency should be higher for the sampling reason, should be higher than message frequency. This is the FDM signal, M1 multiply C1 plus M2 multiply C2. So let's go for the software. At the first glance it sounds somehow scary, but if we become familiar with the concept of that, it is easy. Let's start from scratch. We do need our cosine. This is the signal. By default it is sine. There is no cosine, so we use sine with 90-degree shift in the phase. This is the frequency, amplitude, and the sampling number. So very good. This is the carrier, so message 1, carrier 1, message 2, carrier 2. For the sake of simplicity and make it easy to troubleshooting at each step, I added an oscilloscope spectrum analyzer. This one is just a device, is a block that shows us the output, but if we add this block as a Fourier transform function before that, it becomes spectrum analyzer. So this is for message 1, carrier 1, message 2, carrier 2. We're going to mix them to each other. This is the mixer. After the mixing, as I told you, we do need filter. Each one goes to a filter to omit the unwanted part of the frequency, and we'll have the output, and we're going to add them together. What we've done so far is exactly equal to this: filtering, suppressing the upper sideband, and add them together. After that, we know that nothing is ideal in this world, so there is a Gaussian white noise which adds to the signal, and we're gonna consider it as an AWGN channel. This is the receiver, so the signal is very noisy. We need to remove the noise, and this act is down conversion. We need to multiply again to the main carrier to find our initial signal, and during this filtering and I don't know, the noise, in the real world we have a multipath effect, we have interference, we have distortion. The signal will be attenuated, so we do need amplifier, which I added here, and the final signal should be removed by the filter. So let's take a look at each block. Let me show you how I made them and the final result. So this is the whole thing. Let's take a look at all of them. Very good. So just we do need to do right click. Whatever we need is here. In the signal processing tab, we have waveform generation. This is our signal sign, I don't know, rectangular, whatever. This is the noise, and here this is the filter. This is the first part that we just made them easily without any, I don't know, problem. We can add them together, but just the point is important here is to understand this connection should be directed. Look, each one have different ports. We should connect them to the device by its order. So let's run it and see the result. This is the result of the simulation. This is the initial signal. This is this one, the cosine, and this is the signal, and this is the Fourier transform of that oscilloscope and the spectrum analyzer. This is my main signal, and this is my main carrier. The frequency is 100, and this one frequency is 1000. We can see here, this is the frequency of that. And if we come down, let's see what will happen. This is the mixed signal, so mixed M1, and after mixing we will have this signal. This is the signal here. They come here, they add together, and look, this is the unwanted part that we do need to filter that. So it goes directly to this filter, and this is the output of the filter. We remove this one, and let's go. This is the signal 2, which I filtered. So the interesting part. After adding these two signals to each other, this is message 1, this is message 2, they're gonna add to each other, and the output, the FDM signal, will be this one. This is the spectrum of that, and this is the signal of that. They're gonna go through the AWGN channel, and after adding the noise, this is the received signal. So the signal we send through the channel is this one, and the signal we receive is this one. Completely noisy received signal. What should we do? We know the range of frequency of these two, and just we do need a filter, a band pass filter, to just cover this frequency. So after filtering, the signal we will have is this one. This is the signal we sent. This is the noisy one, and after filtering we are still somehow unable to recover the main signal, but it is the same. So we need to add the down conversion, and we'll have different harmonics, additional harmonics, because now we have two different frequency components, and we're gonna multiply another cosine to them, and each one will result into different. So in the end we will have 4. This is down conversion and 1, down conversion message 2, and we just do need filtering. After filtering and amplification, we'll have this signal as the main signal M1, as the main signal M2. So let's stop it and have a closer look at what will happen. We sent this signal to the channel with this spectrum, and the signal we received mainly is this. What is the receiver is going to do? The receiver is going to compare the similarity between the signal that it received and the signal it desired or it expected to receive. And as long as they are matched together, the receiver will consider that as the data. And this is the point that I wanted to mention. Never the signal that's transmitted will receive to the receiver in a same waveform or in a same form. So this is the whole concept of AWGN channel, frequency division, multiplexing, and the mixing, and whatever that was valuable to mention during this video. I hope you enjoyed. Bye everyone.